Okay, we're gonna start this webinar today and give the opening. And ladies and gentlemen, good afternoon and good morning, and welcome to attend the Green Hydrogen APAC live webinar, a series opportunities and challenges establishing the hydrogen supply chain across the APAC. And this webinar is in partnership with the Connecting Green Hydrogen APAC, the physical event in Australia, produced by the Leader Associates and powered by the Green Hydrogen Council. My name is Brittany and conference producer of the Leader Associates. And today I will host this webinar for you and with the second insights on the Asia Pacific region's emerging hydrogen industry and market. And last time we've learned that there's been a great potential for upcoming the hydrogen business in these regions, different sectors as renewable energy developers like H2U, technology providers like J-Power, and infrastructure owners like AGIG, especially in Australia with great renewable resources to produce and supply renewable and clean hydrogen at scale, which would satisfy the countries like Japan, South Korea, Singapore, and China. And their growing hydrogen demand from the transport and fossils. Meanwhile, it will bring many opportunities for the energy sectors to build up the international hydrogen supply chains across the ocean. Okay. Therefore, this webinar will help you understand more about how to connect the different sectors for a hydrogen supply chain. And it's really our pleasure to get the speakers to share their knowledge and insights of the hydrogen in APAC. And let me introduce the topic here. Okay, let's see. The first topic is the hydrogen energy market updates and opportunities in APAC, which will bring you all an overview of the emerging hydrogen market in this region. And it will be presented by Dr. Minko Lee, a senior research analyst from the Rystad Energy. And the second name is scaling up the green hydrogen and ammonia production for domestic supply and export. Apparently, it will bring you the knowledge about the green hydrogen production and the unique role of the green ammonia in hydrogen supply chain and export. And it will be presented by the Phil Oning, the hydrogen transformation partner from the world. Let's go to the third one here. It's the role of the hydrogen in our future energy mix, which is presented by the Sam Lee Mohan, who is a manager innovation projects from the ATCO Australia. It will bring the significant knowledge about the hydrogen application in infrastructure, decarbonization, energy distribution, and the microgrid. At the next, it's a large-scale hydrogen storage, the missing link to a green hydrogen future. It's really a hard issue, but not in hydrogen, but not only in hydrogen industry, but also relates to the solar, wind, and energy storage. And this knowledge will be presented by the Cassie Lapu, the managing director of the Argent Underground. And the last one is facilitating hydrogen energy export in APAC. It will focus on the hydrogen energy export across the ocean, which will be the key role played by the maritime industry in upcoming hydrogen future. And it will be presented by the Martin Carolan, the Executive Director, Corporate and Finance from the Global Energy Ventures, GEV. And in this webinar, every speaker will have 15 minutes for presentation, and if there is time left, it will have a Q&A session for the speaker. And if you like to ask a question to a certain speaker, please write it down to the Q&A box. I will transfer your question to the speaker for answer. And if you get the technical issues of the voice and the display, then please don't worry too much. Just mention it under the chat box, and we will try our best to support you. And this webinar's recording will be released on YouTube next Monday for your review. And before the start, I'd like to briefly introduce who we are, the Leader Associates. It's produced the creative event experience that meet our clients' strategy goals We're committed to provide professional business services to our clients and build the interactive communication and networks to share knowledge and experience globally. Nowadays, we have hosted more than 25 events across Asia Pacific, South America, Africa, Central Asia, and Europe. And we're honored to have a network of over 80,000 industry professionals covering the wind, solar, energy storage, and green hydrogen. And now we are here. Hopefully, you really have a lot of time to enjoy this hydrogen think tank. Now let's get started. Okay, the first topic is hydrogen energy market updates and opportunities in impact, presented by the Dr. Min Li, the senior research analyst of the Rystad Energy. Hi, Dr. Min.
Hello, hi Grace. I think I can hear myself on your one, but yeah, I'll start sharing my screen very soon.
Yes.
All right. Can everyone see my screen now?
Yes, sure, perfect.
Okay, great. So it is very good to be here with everyone coming into the webinar, taking a look at green hydrogen, especially in the APAC region as well. So my name is Min Li. As Brace has mentioned, I'm one of the analysts here at the renewable energy team in Rystad Energy, which is one of the knowledge house. And we are an energy knowledge house. We're looking at the entire energy sector, from renewable energy to power, but also very much also in the oil and gas sector as well, and looking at it from from a very holistic view of the whole industry and see how things are moving, especially in the energy transition part. So the presentation today basically taking a look at the current state of the market for the hydrogen, especially for green hydrogen, and also we can see where APAC stand among all these new announcements and plans and ambitions and so on. But before we start, I just want to basically paint a picture of what is renewable sector look now globally. So if you take a look here at the map, each of these bubbles represent a renewable asset, whether it is a solar farm, a wind farm, or a storage facility in the form of pump storage or batteries. This is what you see. Basically, you have three main centers of renewable energy in the world. You got the Asia region, you got Europe, and you got North America here. But you can also see a lot of assets coming up in South America, in Australia, and so on. But here's is what you will see when you start taking a look at how's the situation, how the industry and sector will change from 2025 and 2030 onwards. You can see the emergence of bigger projects here in the Asia region, Central Asia, North Africa as well. But also, if you take a look at the blue part here, which is the hydrogen electrolyzer, you do see these projects start to come up more and more in 2025 and 2030, especially in Europe and in Australia. So now we will take a look at, closely more in terms of the growth, of course, and where this hydrogen kind of look into the general growth of renewable energy. If you split it by different continent, you do see that, as I mentioned before, North America, Asia, and Europe still have very strong growth for renewable into 2030, spreading across offshore wind to solar, but also a little bit of growth in onshore wind that we see as well. And if you do look at, the other region like Africa, South America, and Australia, they do look a bit small here, but that is, with respect to the bigger region. And if you look on the scale, we are talking about, 100 of gigawatts growth here among these regions. A little bit closer look also in the Asia region as well, where is the main growth coming from? Of course, you always have to talk about China, but you do see growth coming out in other countries, such as Vietnam, for example, South Korea, Japan, Philippines. Of course, you already see the growth in Taiwan with a lot of offshore wind development and some of the new bigger solar farm that's coming up in the country. And you cannot disregard India. You already see how much growth it has in terms of solar coming up with a lot of also major players looking into doing M&A in this market. Now you might see that, okay, we have hydrogen electrolyzer here and it still have a very small growth among all the region, but you do see it coming up in Europe. And actually, when you take that part out of the mix here and just take a look at hydrogen electrolyzer, how does we see it growth in the future? From the current project that received, financial close, FID, and the current project that have very much in advanced stage, we still see them in a smaller scale. And that's why, until 2025, with cost still high and those challenge, we see it only reaching about 6 gigawatts, but it can really ramp up after that, and especially reaching quite high number in 2030. Keep in mind that, some of this target and committed spending from countries in, especially in Europe, for example, looking at 40 gigawatts by 2030, we still see the cost being a challenge here, and we might not be able to get there in terms of the target. So if there is some positive, changes in the cost of electrolyzer, but also the cost of renewables decreasing, then perhaps we can see this to grow a bit more. But we do see a lot of countries already have committed spending in this regard. We haven't seen much in terms of how they want to split this spending, whether to incentivize the demand part or how much they're going to give in terms of grants. For example, we do see some grants coming out of Australia, but in terms of other region, it's still waiting to see how exactly these billions will be spent. Taking a look here, if you plot on those hydrogen electrolyzer facility on a map, like we did before with all the other forms of renewable energy, we do see the center here being Europe, in Australia, and a few more in the Middle East and so on. But really in contrast with what we see before, in terms of the renewable center of the world in North America and in Asia, we don't have a lot of currently, announced and committed project for hydrogen electrolyzer in the Asia region and North America. In North America, of course, you with Biden coming up now, might be able to see a bit more, but still blue hydrogen represent a very strong competition there. In Asia, you do have quite high cost of renewables in certain countries like Japan, like South Korea, and that's exactly why they are looking into other market in terms of an exporting scheme, importing actually. One of the center that we see is somewhat missing in this picture is China. Currently, there's only about 1 gigawatt size project in China that has coming up. A few other projects are in the 100 megawatts range and so on, and these projects are quite numbered, but what are coming up now at the end of this month and already in the plan for certain province is the next 5-year energy plan. And this is what we see, what we think will be a lot more facility being announced after this plan, especially in regions such as Inner Mongolia, where you have very huge, basically it is a stop state in terms of renewables in the world, both good resources for solar as well as wind. So then, taking a look at what is happening now, then taking a look at the past year, we went through a pandemic. And actually, if you take a look at how many projects of a hydrogen electrolyzer was announced last year, actually, you're reaching into the 40 gigawatts mark, which in terms of a total pipeline that we're currently tracking here, right, that is about 75 gigawatts. Then that accounts for more than 50% of the pipeline coming in from last year. So you really see that the hydrogen electrolyzer and green hydrogens really kick into plan in the past year, especially after the pandemic. You can see here in terms of the spread of where these projects are. Australia with a huge number of pipeline coming from very big development over there. You also see a lot of development coming out of Europe, but also South America, in Middle East, as well as in Asia. You do see this start to come up a lot more. So this is what we continue to track, and into 2021 as well, we already see some big announcement, especially in South America, where in Brazil, for example, they just announced a project. And exactly this is where we see, when we take a look at the top 10 projects currently in the world, when you look at this, I think 4 or 5 projects here are coming from Australia. Of course, you got the Asian Renewable Hub, you got Murchison project, but you also have the Pacific Solar or the H2 Hub in Gladstone as well. In other region of the world, do have the Beijing Jingnan, but we believe this will come up in phases. You do have the base one, which I just mentioned, a project that was very recently announced by Australian company called Energix Energy in Ceará in Brazil. And you do also see a few other projects in that South America region, like HyX, for example. Outside of that, some projects in Europe, like Aquaventus or the Greater Copenhagen area planned by Ørsted, or in Saudi in NEOM. So a lot of multi-gigawatt projects here, but you I think we all agree that this project will be coming up in later in this decade, or if not, past 2030. And when you look at the size, how it's going to change in this market, we do see the majority of the smaller project will start to come up first, and then slowly you will see bigger development as the supply chain more mature. You start to figure out how this incentive works and things like that. And actually this picture is quite resemblance of other form of renewable energy, where you start from a small base, especially in the solar side of things. You now do see most of the solar farm around the world in the 100, 200, 300 megawatt range. So looking at outside of the projects, looking into more of electrolyzer suppliers around the world. Now, just to keep in mind, because all these projects are in very early stage, they are mostly preferred contract. But if you plot them, the top 8 supplier in the world here, you do have ThyssenKrupp, Siemens, Hydrogen Pro, Hydrogenics, who is now owned by Cummins, Cockerill, who has a partnership there with Qingli. You got Nel, ITM Power, and Sunfire as well. You do see a bit of mismatch in terms of pipeline here, with Siemens and ThyssenKrupp having a very big pipeline. However, those two main projects that contribute to this pipeline, the Murchison project and NEOM project, whereas they are still very much in an early stage. So if we do take those out, here's what the pipeline look like. And most of these projects will be below 500 megawatts. You do see a little bit change in terms of ranking here, but we will see continue forward how that will process. Also note that you might see here there's mainly all European players on this chart. A lot of it, actually is a mix between PEM as well as alkaline at the moment, with Sunfire being one of the only company that doing the SOE type of electrolysis. But Hydrogen Pro here partner with an alkaline manufacturers, Tianjin in China, and they're actually based in Norway. So then, taking that outside, I think one ending note that I want to look at in terms of electrolyzer as well is, if you look at the current capability of manufacturing, probably they sum up to about a little bit more than 3 gigawatts. So it's still very much a chicken and egg, whether there's enough committed projects there to really push this supply chain going forward as well. And that is actually one of the major factor that we think can influence the reduction of costs in green hydrogen. If we take our insulation case here of 6 gigawatt by 2025, and somewhat around 30 by 2030, and we assume a certain learning rate, not so different from onshore wind or from solar. And of course, this learning rate varies, depends on how advanced each of these technology is. Taking a look at that, we do see the electrolyzer cost to decrease in 2025 or 2030, but still one of the main key factors remain to make green hydrogen competitive here is the cost of the renewables that feeding the electricity to it. We do see LCOH of hydrogen, reduced below $2 mark, but that means you need to have, let's take just a case of a solar PV farm attached to it, you need to be below, $0.50 per watt there in terms of capex to really facilitate this LCOH decrease. So that is a very quick overview of the market here in terms of hydrogen electrolyzer. In APAC region, we do have a lot of growth, and hopefully we can see some more production facility for green hydrogen coming forward into the future as this industry start to mature and mature more. Happy to take any questions.
Thank you, Dr. Ming. It really showed us an overview of the hydrogen market and significant trends. And here we got some questions for you. The first one is, it's it's about Vietnam. How valuable is hydrogen as a source of the renewable energy in Vietnam, given its huge untapped solar or wind potentials?
Thank you. Thanks for that question as well. I have background in Vietnam, so it's a country that close to my heart. And we do see very recently very strong growth in renewables in Vietnam, installing 5 gigawatts in 2019 and another 4 gigawatts in terms of solar in 2020, and continue we see that number going forward. But what you need to take a look at Vietnam, it is still a growing country, a developing economy. So that means the energy demand, we continue to see it increase a lot. So it might not be the time yet for Vietnam to move into green hydrogen, but rather just do normal renewable energy, solar, wind, just to supply the demand. What we see in the world where countries with a lot of these green hydrogen plant is country where the demand is not really increasing. They have very cheap renewables in terms of very good solar resource, very good wind resource, and so on. And then green hydrogen represent an opportunity for them to export renewable energy into other region.
Okay, the second is what do you think, what kind of the emerging factors and technology and that would drive down the cost of the renewable hydrogen production?
That is also a good question. As I presented in my last slide, a lot of it will be due to how much technology can improve in electrolyzer to drop down the cost, and how much actually electrolyzer facility can be installed to basically also have that economy of scale backing it up. But the major part is the cost of renewables. So if you do have cheaper cost of renewables, you can see drastic decrease in the price. And factor in, let's say if you use electricity from the grid, for example, and if those electricity fitting into the grid is more renewables, and if it comes from a cheap source, then we can also facilitate this hydrogen electrolyzer going forward. But very much now in the near future, how we see it is they will require incentives from the government to basically kickstart the industry, not unlike what we see, in the solar and wind sector before. Things like carbon tax, things to incentivize this supply chain, as well as the installation and the demand. See how that play out.
Okay, and we got another question from the Q&A session, live Q&A session. The first one is, electrolyzer technology has been around for a long time, and why do you think learning rates will drive the caps costs down by so much so quickly?
Yep. So alkaline technology has been around for a while, of course. We do see some of the new, announcement and some of the new technology coming in alkaline, whether switching out the alkaline liquid or, having a switch of liquids here to reduce the energy use. For PEM, of course, actually they haven't been around for as long as alkaline have. In the PEM membrane, you do see the use of some, high cost material, rare metals like platinum and so on. And there are active research in order to go away from that. So if we manage to do that, the cost can decrease. and SOE is still very much in early stage. The ceramic electrolysis technology is still very early stage, but it does have its advantage in terms of the end use, given that the temperature required to run this process is already high, so you don't have to go to step up for, again, the temperature in the later stages to facilitate certain application. We do see Sunfire already in partnership with the aircraft industry to look into synthetic fuel. So we'll see how that goes.
Okay, thank you, Dr. Ming. And I found that there are another two questions from the Darren Jarvis, and but we have to catching the time to the next speaker. And if you like to answer the question, and you could write down the answer on the Q&A panel. And thank you very much.
Thank you.
So, and now we will let's welcome our second speaker, Phil O'Neill, as a hydrogen transformation partner of the Worley, to bring the second speech about the scaling up the green hydrogen and ammonia production for domestic supply and export. Hi, O'Neill. Okay, we got it.
Thanks, Bruce. You've got the screen?
Okay, perfect. Let's get started.
Great. Thanks for the introduction, Bruce, and welcome everybody. So my name's Phil O'Neill. I'm a hydrogen transformation partner for Worley, and Worley is an Australian headquartered advisory, consulting and engineering company, and I'm one of more than 48,000 people that we have around the world working our business. And my role, it seems like a bit of a strange title, but it's actually working closely with customers and advisory roles during all stages of their hydrogen projects, trying to help them find the best way to progress forward with those projects. So I'd like to start my presentation by acknowledging the traditional owners on the lands on which we meet. In my case, it's the Wathaurong people who've cared for the land in the Geelong region for tens of thousands of years, including where I live, work and play. And I'd also like to pay my respects to the elders past, present and emerging, and extend that respect to any Aboriginal and Torres Strait Islander people present on this call. So where are we at with green hydrogen and ammonia? So old is new again, right? So this electrolytic hydrogen and even green hydrogen and ammonia is not a new idea. So this plant is in Egypt on the Aswan Dan scheme, and it has a electrolyzer and ammonia production plant. And it's just been recently decommissioned and replaced with a gas fed plant. So it's a strange world we live in. And this is about 165 megawatt system, so pretty large compared to some of the demonstration projects we're working through at the moment. So, but in Australia, there is some things happening. There's some pilot scale projects that are in implementation. So there's an AGIG project in Adelaide. Gemini has a project in Western Sydney. Toyota has a eco park in Victoria. And ATCO has a microgrid project in Western Australia. And you're going to hear from Sam from ATCO later in this webinar. So those projects are implemented, and most of them, I think, are operating or very near to operating. We also have a few demonstration scale projects that are moving ahead, and those are targeting some early niche markets. So some examples of those are H2U, who are producing ammonia in South Australia for local supply. Yarra in the Pilbara, who are looking to blend green hydrogen into an existing ammonia plant. And FMG are looking at testing a fleet of buses in Western Australia, hydrogen buses. But then backed up behind these, we have a whole raft of larger scale projects. And I guess they range from what you might call ambitious to audacious in scale. And as an example, there's no less than 4 projects announced for Bell Bay in Tasmania. And those big names involved, such as Woodside, FMG, Origin and Grange Resources. And in Gladstone, in central Queensland, again, Origin and then H2U and Stanwell have all revealed projects in that area. But the award for the largest announcement must surely go to Western Australia, where Infinite Blue Energy, BP, Hydrogen Renewables Australia and the Asian Renewables Hub have revealed plans for 1 gigawatt, 1.5 gigawatt, 5 gigawatt and 23 gigawatt projects respectively. And to put this in perspective, the entire East Coast electricity market has around 50 gigawatts of generation capacity. So these are massive projects and going to demand a massive build of renewables. So what is needed to get these proposed projects moving? So I guess there's two things. One is getting the production at the right cost, and the second one is getting the offtake at the right price. So at the moment, we're kind of stuck in this divide between high volume offtakes that can drive scale and cost reductions in the industry, but with low value. For example, natural gas blending, and low volume but high value applications such as heavy transport. So in other jurisdictions, this is being addressed, such as in the European Union, with generous capital subsidies and the potential creation of high value markets. So in Europe, for example, they can use green hydrogen from offshore wind to displace natural gas in refineries and earn a credit towards their renewable fuel scheme. And that substitutes for second generation biofuels, which are actually pretty expensive to source at the moment. But let's put all that offtake talk aside, because I'm going to focus on the production side for now. So why green ammonia? So ammonia is one of the most common chemicals in the world, and there's about 200 million tons of it made every year. And it's used to manufacture fertilizers and other chemicals such as ammonium nitrate explosives, and is also used in water treatment. But what is under development now is ammonia as an energy vector. So locking the hydrogen molecule into ammonia to increase the density and transportability of hydrogen. So ammonia has a lot to recommend it as an energy carrier. It has an international network of infrastructure and ships, as well as a depth of industry knowledge in its production and transport. It can be used directly as a fuel to replace coal in power station boilers, or to fuel turbines and reciprocating engines in power stations and ships. But there are also challenges. There's a toxic chemical, although its safe transport and use is well established in an industrial context. You have to think about what happens if you start spreading it more widely than that. And ammonia and its direct use in fuel cells is yet to be proven, although it is under development. Currently, a cracking process is required to create pure hydrogen for fuel cells. The process is still emerging at scale. So what are the opportunities for production cost reductions? So this is similar to what Dr. Min showed before, but in a pie, because I like pies. And this simple graph shows the makeup of the cost of hydrogen production. And straight away, it turns your focus towards exactly what Dr. Min said, the power. Equipment cost is also significant, and operational costs contribute. But you can see that water is really in the noise, if you can even see that green sliver on the chart there. So the cost of power and the amount you use to make hydrogen is a big influence on your final cost. So in general, cheap electricity is available at lower capacity factors. For example, avoiding peak pricing periods or direct connection to a solar energy in the Australian context. Combined wind and solar plants give a higher capacity factor in most locations in Australia. Behind the meter installations at wind and solar farms can avoid costly transmission fees, but you have to think about where your hydrogen customer is. You'll need to deliver your product to where it is needed. Grid-connected projects can take advantage of electricity market dynamics and commercial instruments, such as renewable energy certificates, to increase the capacity factor of the plant, if enough grid capacity exists. Grid augmentation can be expensive and delay project execution, so sometimes it's better to be independent. And note that as you reduce capacity factors to reduce your electricity costs, your equipment costs will go up, as you have to produce the same amount of hydrogen in less operating hours. And a significant portion of the operational costs are stack replacements after 60 to 80,000 hours of operation. Much work is occurring to make these membranes last longer and give higher efficiency, but it's also traded off against the initial capital costs. More stack area equates to higher cost, but higher efficiency and potentially longer life. As manufacturing costs come down, we can expect efficiencies to improve as more stacks are installed for the same output. In the short term, more efficient electrolyzers means lower power costs. It can actually be worth paying more to use less power. And I'll leave the discussion of hydrogen storage to Keith later in the webinar. So let's move from pies to donuts. So this is showing the equipment costs for hydrogen production by electrolysis broken down. In the inner ring, we have classified the costs into base, balance of plant, and installation, build up the total direct costs, or TDC. And to clarify, to these costs, we need to add owner's costs, site preparation, insurance, contingency, etc., to get to the total installed cost, or TIC. So the outer ring shows that the base costs include electrolyzer design, stacks, control and electrical, and purification, and this makes up around half the cost of the electrolyzer equipment. However, these definitions are a bit fluid, and KOH systems, transformers and rectifiers, and purification can mean base or balance of plant scope depending on the manufacturer's or the project developer's preference. In the balance of plant section, compression and installation make up the greatest portions. So if you want to reduce the capital costs, you need to target the stack, of course. These are modular, and modules in factories are getting bigger to reduce costs. But you also need to consider the balance of plant and other costs, and consider questions such as, what is the best scope boundary between electrolyzer vendor supply and balance of plant? Can you drive lower costs through doing all processes in a replicable fashion at modular scale, for example, 20 megawatts? Or once stacks get too big to factory assemble, does the site assembly cost and quality considerations cancel out some of the scale gains? Or can you make gains through consolidation of balance of plant for gas treatment, electrolyte handling, storage, and compression? So this work is this area is a work in progress, and a clear path forward has not yet been established. I'm confident some significant gains will be made that will drive hydrogen production costs down. Turning to ammonia plants now, this is an established technologies. So what are the levers left to us? There are at least two that are being worked on. Larger scale to drive cost reduction. The largest capacity is now around 4,000 tonnes per day, equivalent to around 2 gigawatts of electrolysis capacity. This is a result of steady increase in ammonia plant capacity over many decades and much learning. These superscale plants aren't for everyone. You'll need a solid offtake and large backers to make this happen. Innovations in plant flexibility to match hydrogen production can reduce overall costs through less hydrogen storage and lower capacity factors, allowing lower cost electricity. Electric drives and careful control of the synthesis loop reaction temperature can allow faster ramping and a lower turndown. So having screwed down the costs, where do we focus to scale up green hydrogen and green ammonia in Australia? So we want to aim for the bullseye of high value and large scale, bottom left-hand corner. So the highest value is in remote power. Hydrogen could offer competitive long-term energy storage in diesel-supported renewable systems and a pathway to zero emissions through a pure renewable and hydrogen storage solution. As the amount of energy that needs to be stored increases, battery storage becomes increasingly expensive. And in remote systems, there are daily and seasonal production and demand aspects to be balanced. However, these systems are often small, with mining being an exception, so the potential for scale up is reduced. Heavy mobility appears to offer high value and potentially large scale, particularly with mining trucks and other back-to-base fleets. In fleets, hydrogen production and refueling costs can be shared across many vehicles, removing one of the key barriers to uptake. However, it is a big commitment to convert a whole fleet over to hydrogen, and many demonstrations will be required before it's bankable technology. So the purchase of individual trucks is not going to get us to scale, but can create the demonstration pathway. Export is a real opportunity, subject to those offtakes I mentioned earlier. With ammonia as the vector, energy could be shipped from Australia to other nations to supply their low emissions energy needs where their domestic resources are limited. And ammonia as a product, energy storage, shipping, and rail freight could also offer value and scale, although rail freight still has some technical challenges to address before becoming mainstream. Ammonia can clearly offer large scale at a single location. Energy storage and rail could be more distributed to match the grid support requirements and freight depots, but is still with significant demand at each, likely to be several megawatts, tens of megawatts. So in closing, there are many opportunities out there for green hydrogen and green ammonia. So let's get after them, turning projects into realities, scale this industry and drive down costs in this virtuous cycle. Thanks, everybody.
Hi, Phil. Hi, Phil. Thank you, Phil. Thank you, Phil. You really showed us great insights of the green hydrogen and green ammonia production and their upcoming trends in this emerging energy supply chain. And also here we got some questions for you. The first is, what's the size of the future PM electrolysis market, and what's the latest technology trend for the electrolysis?
Okay, thanks for that. Definitely the dominant technology in terms of large-scale plants at the moment is alkaline. It's offering lower costs and higher efficiencies at this time. But PEM technology in the future could offer, depending on getting production costs down very quickly, could offer even better efficiency than alkaline at a comparable or maybe even slightly cheaper cost. Let's shoot for comparable. And potentially offer some flexibility advantages and allow, as I mentioned about low cost electricity, allow you to respond to electricity signals and potentially play different electricity response markets to lower your overall cost of energy into the plant. So in terms of the latest trends, well, the solid oxide electrolytic cell has had some news this week with Heldal Topsoe announcing developing a factory to produce those cells. But the ongoing theme is of fast development and fast scale up, and hopefully prices coming down very quickly.
Okay, thank you. And the second is green ammonia. How does one clarify green? Is green hydrogen production with nitrogen or single section in grid power good enough to clarify?
Yeah, so as far as I'm aware, there's not actually a definition of green ammonia yet. There is an emerging definitions of hydrogen, low carbon hydrogen, which is effectively proposed to be based on taking blue hydrogen from natural gas and sequestering a portion of the emissions. I believe it's 40% of the emissions, maybe 60% emissions, sorry, leaving 40% still emitted. So that may flow through into ammonia as well, where green ammonia is defined the same way, or low carbon ammonia is defined the same way. Certainly what we found and what we've looked at is that in most Australian states, if you start taking electricity from the grid without any kind of green certificate, your emissions intensity of your hydrogen and ammonia very quickly becomes higher than that of natural gas based hydrogen and ammonia. It doesn't take a very high percentage to get to that point.
Okay, thank you, Phil. And here we got some questions from the live Q&A box, and you can see there is a question from the Darren Jarvis, and he asked about how can installation only be less than 25% of the capital cost of all electrolysis, and what benchmarks are used to estimate this, given and there is nothing at any scale in Australia?
Yeah, that's a good point. There certainly hasn't been anything of that scale built, of large scale built anywhere since, well, the 1960s or something. And yeah, those benchmarks are based on estimates because yeah, projects haven't been built. The electrolysis plant itself is not a complicated plant to install. And compared to, you know, there's not a lot of stick. Hello?
Sorry, carry on.
There's a lot of equipment comes fully built up, including a lot of it's very modular. Lots of the equipment is assembled rather than constructed on site. So yeah, we'll certainly be learning as we go along about what those real costs are. But yeah, that's where it's at the moment.
Okay, thank you, Phil. And here is, we got another question. And how are the companies like Worley and others evaluating and selecting the companies to assist them in their logistics? Like a freight forwarding and the needs, what support is given to transition them into its new market.
So I guess if I understand that question correctly, it's asking about building ports and storage and logistics facilities. So we're certainly doing that for companies who are developing greenfield type opportunities, and we're certainly assessing lots of different locations for those facilities. And there's a whole supply chain analysis there, looking at where is your renewable energy resource, where's the best place to locate your hydrogen production, where's the best place to locate, if you're exporting, where's the best place to locate your carrier production, how do you connect them, and then how close to the port do you have everything so that you can easily load, but is the land available, what's the price, and all that type of thing. So yeah, we in terms of taking the question one step higher about companies who are looking to transition in their businesses, perhaps from a carbon intensive business to a low carbon business. Yeah, that's certainly something we're advising and helping customers with as well. And I guess the example of the oil refinery I gave earlier, or there's many of those, looking at those sort of opportunities, those are the kind of projects that we're involved in.
Okay, thank you, Phil. Thank you, really thank you very much for your presentation. And we think Worley will play a key role in Australia's energy industry, and especially in the hydrogen industry. Thank you very much, Phil.
Thanks, Bruce. Thanks, everybody.
Thanks. And now let's turn to the next speaker. But we found that the APCO's speaker, Sam Limuhan, was offline. So I'd like to ask Mr. Case, his love group. Hi, Case. Hi, Case.
Hi, Bryce. Good afternoon, everybody. Let me share my screen.
Okay, let's get started.
Is that working okay?
Yes, perfect. And shout it to a screen, and it's
okay. That's full screen now, is it?
Yes.
Okay. Okay. Good afternoon, everybody. Yes, I'd like to move on from the other two speakers and talk a little bit about the imperative for storing the hydrogen. I'm speaking today on behalf of Ardent Underground, a new startup company. No employees at all, so it will be a while before we catch up to Worley, apparently. It's a joint venture of my own company, ITP. ITP is the smallish renewable energy engineering and consulting group of companies originally out of the UK, with a fairly strong presence in Australia, also in India, a little bit in China. We've partnered with a company called Abergeldy Complex Infrastructure, which is an Australian-based company that does a lot of, as you can imagine, infrastructure, but tunnelling and specifically blind bore shaft drilling, but also bridges and ports and things like that. So the missing link is the way I'm presenting hydrogen storage. So look, we've alluded to the future, particularly like Phil's target chart there and the high value, high volume that we're all shooting for. But the point, of course, is that for all of these applications, be it vehicles or dispatchable power on large or small scales, or ultimately this vision of the export thing, which I think we're all agreeing that is the ultimate vision, certainly for Australia and indeed the world. But in every case, we're talking about wind and solar power production. It is intermittent. So is the hydrogen production. It it is not realistic, I would argue, to think that we would have battery systems after the PV in order to run the electrolyzers continuously. That doesn't actually make sense. But every usage for hydrogen requires a stable flow, or indeed an on-demand flow, certainly power generation, vehicle refueling, and indeed, in the case of the export, what's needed is a stable flow of hydrogen to feed, for example, the ammonia production. And I think I certainly agree that ammonia production seems to be the most sensible export vector. But even if it's cryogenic liquefaction, that's also going to be something that won't run intermittently. So we know that hydrogen itself has a low density. It needs high pressures for storage. We certainly have pressure vessels for this, but really, if we're going to think about this long-term, large vision for hydrogen, we need storage that's on a commensurate scale to the vision of production that's talked about. So let's put that into context. A Toyota Mirai, an available fuel cell vehicle, has a very high-tech carbon fiber-based tank, stores maybe 4 kilograms of hydrogen. If in Australia we wanted to support all the existing ammonia production existing today with, say, a 2-day buffer, well, that jumps to 3,000 tonnes of hydrogen that would need to be stored. If we look at all of the currently proposed large-scale export projects and said, well, they might need a 2-day buffer, that's 23,000 tonnes of hydrogen that needs to be stored at any given time. And then if we went on and said, look at Australia, what if we provided 30% of our electricity and we wanted that available for a week? And similarly, what if we move Australia's transport energy? It's a very big and, I suppose, tense discussion to think how transport is going to evolve in a decarbonising world. There's certainly people who would argue it's all going to be battery vehicles, but maybe it is for intercity commuting. But if you look at Australia, for example, we've got a huge need for long distance transport, not to mention the aviation and the shipping. So even if we went with, say, 30%, doing that with hydrogen, that's 100,000 tonnes that needs to be stored. So to put this in a sort of bubble plot map situation, it's a logarithmic scale here, and the diameter represents the daily hydrogen production. So beginning with our existing ammonia plants, and you can see that's already a substantial amount of hydrogen, but of course that doesn't need to be stored. It basically goes from a steam reforming of methane based system in a continuous process straight into the ammonia loop, and ammonia comes out. So there's no actual present need to store that hydrogen. But of course, if these plants, as they do tend to contemplate, move to green hydrogen, the story changes. If we look at all of the announced projects, this begins to be the picture, and I've probably missed a few because it's such a rapidly moving field that we frequently hear new announcements. But as you can see, scattered all around the country, the present and growing need for hydrogen storage. So what can we do to store hydrogen? Well, of course, there are pressure vessels, large and small, but they're not going to get us too far, really. One of the best and most cost-effective solutions that is proven is the idea of a salt cavern. This is a technology, for those of you who are familiar with it, you'll be familiar with it. For those who haven't heard of it, it's quite a surprising thing to think about. It's done at considerable scale in Europe and in North America for natural gas and oil storage. And the basis of it is that there's large underground salt deposits, depending on the geology. They've occurred over millions of years. One can bore down and solution mine caverns as big as skyscrapers and store massive amounts of gas. And it turns out salt caverns like this are very good at storing hydrogen and very cost effective. The problem is you don't always have a salt cavern where you want to build your project. In Australia, there's only, or rather a salt deposit to build the cavern in. In Australia, there's only 3, maybe 4 large salt deposits that I know of at least, and they're not necessarily in terribly convenient places. So it's great if you can get it. People have looked at using gas piping in a sort of make a long skinny pressure vessel by having a network of pipes buried under the ground. One can talk about mining out a rock cavern, a lined rock cavern, and in the middle there, an indication that the possibility of storing geologically in aquifers, and the big challenge there is, well, hydrogen does diffuse through many, many things. If it goes down into a geological situation like that, how much will come back? In the salt cavern, on the other hand, it's actually proven to be very good at containing hydrogen. So it's challenging. And what I want to do today, apart from talking about the general background, is introduce you to Ardent Underground's plans, which is to come up with a low-cost, replicable, large-scale, small above-ground footprint approach to a lined rock cavern. And the way we're doing this is adapting a technique from the mining industry called blind bore shaft drilling. And if for those of you who are not familiar with it, it sounds like a reasonable term, but the key point here is that the shafts that are drilled are anything up to 7.5 meters diameter. So the technique is applied in the mining industry to construct access shafts or ventilation shafts for underground mines, and it's a very big drilling process indeed. It can certainly go down to 500 meters, maybe more in the long run, and that gives us really quite a large volume as a vertical shaft, as a hole in rock. In the applications that are applied in the mining industry, the shaft is initially made and then lined with a casing whose job in that application is to stop groundwater running into the mine and also to stop the shaft caving in any way. So there's this technique available that creates a hole, lines it, and at the moment does nothing more than that. So our concept is to take this and essentially put a dome-shaped cap on each end of the casing, backfill sufficient depth at the top, around about 40 meters would be needed, let's say concreting that in order that the rock that's activated contains the pressure. So radially, the pressure is contained by the rock. At the top, the pressure is contained by this plug that's added later. So we're contemplating anything up to 300 bars using this approach. A bit more here on the steps to construct it, a 4-step process, if you will. The shaft is drilled. The casing, well, in fact, the shaft drilling is carried out with the entire shaft filled with water, and the next slide will show a bit more detail on that. Once the hole is in place, the casing is actually assembled by joining prefabricated elements, welding them on, and gradually sinking the casing down into the water by transferring water out of the shaft and into the center of the casing to keep it semi-buoyant. This proceeds until it's finally finished off with the top dome, and then a process of grouting to lock it all in place. So I emphasize again that the idea here is that the casing does not hold the pressure. The casing simply stops the hydrogen from leaking out, and the grouting transfers the pressure forces to the rock. The rock holds the pressure. This gives you an idea, a bit more detail on how the blind bore shaft drilling works. The schematic on the left there shows you the process, the drill string turning a a single very large drill bit at the bottom and a process of air injection into the inside of the drill string, causing a large upflow in the water, and that actually has the effect of lifting out all the rock fragments and bringing them to the top into a settling dam. The picture you can see on the right, well, top right is one of the drill bits. You can see the bigger picture is a coal mine site here in Eastern Australia, and you can see the people in the centre for some scale and some vehicles and the casing elements there. So this is a proven technique in the mining industry, and what we need to do is prove that we can adapt this and hold gas without leakage. So the critical point here really is how much will it cost, and in terms of an installed cost. The storage is really essential, and the cheapest storage will win. I've made the point earlier that nothing really beats a salt cavern if you can get it. It is a very, very large thing. On the other hand, anything above ground, pipe storage, pressure vessels, they're all really quite expensive, and we believe we can target this region here. So sizes from 20 tonnes to 500 tonnes, but any volume above that by simply doing multiple shafts in the one location, and we think we're below the trend. I just point out that the horizontal axis there is logarithmic, taking us from sort of vehicle sizes right out to massive sizes, and so our niche there is the 20 tonnes to 500 tonnes kind of niche. This has not yet been proven, so we're in the process now of working towards the first pilot. Our first speaker today, really outlined the timeline of this global hydrogen industry, and it's a really 2025 to 2030 acceleration of the industry. What we're trying to achieve here is to take this new storage technology and have it completely ready and proven by 2025, so that it can follow along with some of these fairly large projects that are talked about. So we think it's quite a promising idea in terms of the economics. And finally, I'll just end with this slide that just shows a little bit of the background of the two companies that have come together for this initiative. And yes, thank you. And over to questions. Brace.
Okay, thank you for your sharing. And here we got some questions for you. And the first one is, how close are we to have a hydrogen economy, and how will it compare to other renewable energy competition? Could you answer this question?
Oh, sure, I'll have a go at that. That's a very broad question. I guess all the speakers would have an opinion on that. I think the last part of the question first, one should never confuse hydrogen as somehow competing with the other renewable energies. I mean, hydrogen in itself is a way of storing energy from other sources. And I think that leads into a bit of an answer to the second question. It's very, very apparent that renewable energy is the clean energy revolution. It's happened over the last few decades, and it's just growing exponentially and will continue to do so. But what is very apparent now is that given that it's wind and PV, the intermittent renewables that seem to be in the lead, that immediately brings us to the challenge now. If we want to decarbonise all energy use by 2050, which is really the problem we have to address, then we've now reached the stage where storage, energy storage in general, not just storing the gas of hydrogen, but the whole exercise of energy storage is really the most important thing for us to do. So I think effectively the hydrogen economy is really a subset of the renewable energy economy which already has so much momentum. I think it's just going to flow naturally from here. But I think Dr. Min's talk at the beginning was pretty consistent. You know, it's a 2025 beginning, very strong growth into 2030. I do believe it's inevitable.
Okay, thank you. And there's another question. Is there a definition for green ammonia? And does it clarify if the hydrogen is green and ammonia and are produced using?
Yes. All right. I think we had this discussion earlier, didn't we? Actually, the point to make there is that there's enormous amount of sort of work, let's say, in the economic political circles, looking at this concept, mainly on hydrogen at the moment. What's green hydrogen? What's blue hydrogen? What's this color? What's that color? And I guess it's inevitable that we're going to get a range of certification schemes. Different countries are going to do things. Maybe the EU will do something. I know the Australian government's working on it, but we've also got an industry association in Australia working on it. And everyone's going to have their own sort of view on it. And to give you an idea with the green hydrogen thing, you think, oh, well, if I use renewable electricity, make hydrogen, surely that's green hydrogen. Yes, but one of the subtlest issues of all is whether the electricity you use to make your hydrogen is something you've contracted for, and was it actually generated at the moment when you ran the electrolyzer? Was it made in the same place as your electrolyzer? And does that matter? So these are the sort of arguments, I guess, that people are going to have. And then we move on to the ammonia thing. And I have the pleasure to be associated with the Ammonia Energy Association here in Australia, which is a national effort. And, you know, the Ammonia Energy Association is watching very closely and looking to see how will we define green ammonia. It's going to build on the certification of green hydrogen, but as you say, the rest of the energy and the rest of the process has some life cycle implications, and so that's going to be need analysing as well. So I think I don't think it's very hard to really work these things out. But what will be hard is to get all the stakeholders to agree on which one to follow. So that'll be interesting to watch.
Okay, thank you, Case, and thank you very much for your overview of the large-scale hydrogen storage, and it's really great efforts and the contribution on our future energy, and also very thankful for you to answer some questions that people always have issues on.
Okay,
thank you very much.
Thank you.
And now let's turn to the our third speaker, and Sam Level from the APAC, Australia, and he will bring the topic of let me check the role of the hydrogen in our future energy mix. Hi, Sam.
Hi, Bryce. Fantastic to be here.
Yes, it's your turn to get started with.
Wonderful.
Okay,
thank you for the introduction. I'm just going to share my screen, so hopefully that's coming through to you and the rest of those on the webinar. So I'm going to be talking about the role of hydrogen in the future energy mix from an ATCO perspective. And I'm going to draw a strategic picture and then develop that out in terms of practical projects on delivering on that strategy. And hopefully, you know, give some insights into some of the learnings that we've encountered over our journey to date. So just a little bit about ATCO. ATCO operates in over 100 countries. Here in Western Australia, We are the principal owner and distributor of natural gas with 14,000 kilometers of pipelines, servicing over 780,000 customers in Western Australia. More globally, we operate almost 64,000 kilometers of pipeline, $22 billion Canadian dollars in assets. We own port facilities, storage assets, and I just heard my colleague on the previous speaker talk about salt caverns, which we also own and operate in Canada, 5 power plants, and also modular structures and logistics businesses. So quite a diversified portfolio of assets. Just a snapshot of some of the assets. We obviously have Australia's first green hydrogen microgrid, which we commissioned in 2019 in Jandakot, just south of Perth. And we are also working on under construction refueling stations here in Western Australia, as well as blue hydrogen production and blending in Canada, replication projects over in the US as well. But just from a snapshot perspective, we own ports in Chile, Neptune ports, as well as electricity infrastructure, poles and wires, as well as generation assets. And in Canada, we also retail energy. So I wanted to just give you a high-level view of strategies. I'm just going to move this out of my way. As I mentioned, ATCO owns and operates almost 14,000 kilometers of pipelines here in Western Australia and 64,000 kilometers globally. The gas networks is fundamental to our strategy, and it's about preservation of the assets, but also fundamentally with preservation of the asset come decarbonization. So our strategy firmly grows from the core of utilization of these assets, and hydrogen and other clean fuels like biogas plays a fundamental role in the decarbonization of not just our assets, but our energy future. So just a bit of history. In 2016, we developed what was called the Gasola project. And the Gasola project is rooftop solar batteries integrated with a natural gas-fired generator to provide real-time energy balancing. And what that did was it really gave us a solid foundation and understanding of the role of natural gas assets in the future energy mix. The next logical step for us was to grow that out to a commercial scale and really simulate how we can harness spill energy. So how can we harness energy that's created through intermittent sources, solar, wind, etc., capture it, store it, and use it in our existing asset base. So we conceptualized, engineered, constructed, and commissioned the Clean Energy Innovation Hub in 2019. And we've successfully blended 10% of hydrogen in the natural gas microgrid network in Jandakot. As we progress our journey, we are looking at by 2022 injecting hydrogen into the gas network to service up to 500 customers, and then very quickly scaling that up to 5,000 customers, and by 2023 having up to 2% of hydrogen blended in the distribution-wide natural gas network. And in parallel, we are building capability as well as skills in production. ATCO being a producer of energy company, we've conceptualized and designed the Clean Energy Innovation Park, which will be Australia's first 10 megawatt facility, and all with a view of scaling that up to export scale. And in parallel to production, we are also working on transport. So in partnership with Fortescue Metals and the WA government, we are currently constructing West Australia's first refueling station with a view to rolling out more of these to really bring down those barriers, these infrastructure barriers, and also service industrial users as well. So I'll talk a little bit more about that in a few moments. But from a Canada perspective, gas is really cheap, just like in Western Australia. We've taken a very hard look at blue hydrogen, and we believe that we can produce some of the most competitive in the world blue hydrogen. We own production and storage assets, SMR and carbon capture and storage. We own salt caverns as well as the distribution system, port terminals, and with existing infrastructure and trade routes, established trade routes, we believe that we can provide them at really cost competitive. So just to give you a snapshot as well of those trade routes, as well as the projects we are actively working on. Over in Canada, we are looking at blending blue hydrogen in the natural gas network to 5,500 customers under construction. By the end of this year, we'll have first hydrogen flowing in. We're also looking at a large-scale hydrogen production and storage plant. In Chile, we're working on a proposal for production and refueling. Here in Australia, we've developed the Clean Energy Innovation Hub. We are in a joint venture with Australian Gas Infrastructure Group, developing Australia's first 10 megawatt hydrogen production plant called the Clean Energy Innovation Park. And under construction is the refueling station as well. So some of those trade routes that I talked about here, green hydrogen in Australia, using our abundance, the skills capability that we have already developed and continue to build on, established trade routes out of Dampier to Asia, 9.5 days. When you look at blue hydrogen, ATCO is looking at from Kitimat, that's 12 days into Asia. When you compare that with some of the other trade routes in the world, Qatar, 7 Pass, that's 16, 26 days, etc. So we are looking across the value chain and what value ATCO brings in and how competitively we can do this. Importantly is, and I'll touch why we think that's important in a few moments, but just to give you a snapshot of strategy in action, we developed Australia's first Clean Energy Innovation Hub, which is a 23-ton per year hydrogen production plant, which is dispatchable in real time. And it's fully integrated with a standalone power system that's currently operational. The standalone power system, its combined capacity is just under a megawatt of power. And as I say, we've got a dispatchable hydrogen production plant where we produce about 10.8 kilograms of hydrogen per day with 4 hours of sunshine. And again, to the point on the previous speaker, in this instance, you can actually follow through when the electron was produced, how it was produced, how it flew through into converting it from an electron to a molecule. And then on our site, we are then using that hydrogen for blending, testing. We've also got a residential 4x2 home on the site where it's integrated with a fuel cell and providing that essential backup power back into that home. This is a snapshot of real-time data from the system and how it's operating. So on the dials, you'll see on the top solar producing at that given point in time 97 kilowatts. The way the system is designed, it never produces more than what it actually needs. So in any given point in time, if the batteries are full, which you can see in this instance, it's 457 kilowatt hours, pretty much full. The site is only consuming around 90 kilowatts, so we didn't have to produce any more. So at that point, our storage was where we wanted it to be, just under that 8 kilograms of hydrogen being stored in there, so we didn't have to produce at that particular time. And the site was on 100% renewable energy at that given point in time. So why does ATCO think it's feasible? So we developed the Clean Energy Innovation Hub, and we know that hydrogen was produced at that point around $21 a kilogram. The Clean Energy Innovation Park, which is the project that we are now looking at, the 10 megawatts, we know we can produce the hydrogen at quite competitive prices, and for commercial reasons, I won't mention the price on this call. But importantly, it's what does the future look like? And can you actually get down to a commercially competitive rate in the future? We've completed a study that was funded by the WA government in partnership with ATCO. And the pathway is a credible one. One of the bookends that we looked at is even if you had zero cost electricity spill, can you actually produce hydrogen at under $2 a kilogram to be globally competitive? And the answer is no. Even if you had zero cost electricity, you're still at around $3 a kilogram. But do you actually need the electricity to be zero? What are the other major levers like stack performance, cost of capital, capital itself coming down? So when you actually look at the perfect mix of all of these key triggers, the pathway is feasible, and it does actually come down to less than $2 a kilogram. Today, we are competitive with diesel, and in future we'll be competitive with natural gas, both in the East Coast and West Coast. A snapshot of the Clean Energy Innovation Park. It's a 10 megawatt hydrogen production plant producing 4 tons of usable hydrogen per day. The hydrogen will be stored in stationary storage vessels at 300 bar, and we'll be using virtual pipelines to transport the hydrogen to our injection points in the gas network. And the future of the system will also provide essential hydrogen to transport. So we are working with bus consortiums at the moment to provide the hydrogen to transport, as well as working with an industrial user to take hydrogen as well from the Clean Energy Innovation Park. And the future benefits is, let's not forget about oxygen. And as these plants start to scale up and we hit that between 50 and 100 megawatts, it starts to become feasible to liquefy oxygen and transport the oxygen as well, which then offsets your economics and puts further price, brings the price further down. Some timing for the Clean Energy Innovation Park. By the end of this year, we'll have completed our, at the end of 2020, we finished our FEED study. And by the end of this year, we are looking at final investment decision and first hydrogen Q1 2023. So in the spirit of time, I'm just going to race through the next few slides. The Clean Energy Innovation Park, as I mentioned, was funded by the WA government, partially funded, $375,000, of which we couldn't have achieved the outcomes without them. It'll be producing 4 tons of green hydrogen per day, building on our experience, and we are one of 7 shortlisted projects under ARENA's $17 million renewable hydrogen deployment round. From a Canada perspective and blue hydrogen, we are right at the bottom. And as you can see, the only country that can compete with our export price of hydrogen is Russia. And this is blue hydrogen from natural gas and CCS at $8.49 a gigajoule. And this is using our salt caverns and established trade routes for export. This is a snapshot of our Fort Saskatchewan project, where we are producing blue hydrogen and blending it into via a rig that we built here in Australia, a pressure reduction and blending station as part of our Clean Energy Innovation Hub project. So the same technology is being exported and used in Canada, where we are mixing it with natural gas and blending it into the Fort Saskatchewan network. The project's under construction. So I'll leave it there. There's lots of other projects that we are working on, but in the spirit of time, I'll leave it there. Brace, back to you.
Thank you, Sam. Thank you for your presentation. And here we got some question for you. And the first one is, what do you think, what would be the trend moving forward for the green hydrogen in the medium to long term?
Yeah, it's sort of a broad question. I think the gas networks will become fundamental to building domestic demand alongside transport. From a gas networks perspective, it's a sunk asset. It it distributes almost 25,500 terajoules of energy per annum just here in Western Australia. And it's an investment that's already paid for by the end users. It makes perfect sense for us to actually continue to use these assets as part of the future energy mix. And what that means is that there's policy barriers. There's policy that needs to be implemented that allows us to blend and recover accordingly, because early mover projects is coming at a premium price. So these the right policies and incentive mechanisms is going to drive domestic demand. And I see over the next 2 to 3 years, 2 to 5 years, that the right policy and right incentives will drive the domestic demand. And as we start to get the supply and demand economies of scale, we'll start to see more fleet operators investing in hydrogen buses and trucks and mining trucks. So I think transport's going to be it's a low-hanging fruit. And as we start to build out the domestic and really building on the skills and capability, as well as developing those economies of scale to bring the price of electrolyzers down, as well as invest in more renewable energy assets, wind, solar, etc., and more of the coal-fired power stations go offline, I think that balance is going to be fundamental, and those will be the trends that over the next 5 years we'll see that will really drive us towards the export by 2030.
Okay, thank you, Sam. And could you see the question in the Q&A live box from the Josh? He asked about what are the key barriers to go from the microgrid injection to broader gas grid injection?
Yeah, so there's 2 aspects to it. From a technical perspective, it is quite complex. We have what we call commingling. So you have different quality of gases. And retailers generally, we distribute on behalf of the retailers. The retailers get paid based on the heating value of the commodity. So from a technical perspective, it's things that we do on a day-to-day basis. So it's not difficult for us to do it, but there's commingling. And then there's the limitations on the appliances. So all Australian appliances are tested up to 13% of hydrogen, bearing in mind that natural gas already has hydrogen content into it. So you're not starting from a base of 0 hydrogen in natural gas. But with that limitation of 13%, that's why you'll ever hear gas guys talk about 10% hydrogen injection into the grid, because that gives you a safety margin. And then there's a pipeline perspective. So pipelines, we know we can inject up to 25% of hydrogen under current pressures, meaning that hydrogen won't escape through the barrels of the pipe at beyond 25 or below 25%. So that's a technical things that we are working through. From the most significant barrier, if you like, is more from an economic recovery standpoint. So as you're putting premium price hydrogen into the gas networks, the retailers as well as the distribution network operators, on account of gas usage, will have to have an appropriate cost recovery mechanism, because ultimately this will be reflected in tariffs. So whilst companies are all for decarbonization of the networks, the right policy has to be put in place in order to enable a balance between cost recovery and sustainable cost into the future. So I hope that gives you some insights into that question.
Yes, perfect. Thank you, Sam. Thank you for your presentation and the answers for the questions from our audience. And we are going to the next speaker. And thank you very much.
Thank you.
Thank you. And now let's turn to the last topic about the facilitating hydrogen energy export in APAC, presented by Martin Carolan, the Executive Director, Corporate Finance from the GEV Global Energy Ventures. Hi, Martin.
Hi,
Good.
Thanks, Bruce. Thanks for having us.
Let's get it started.
Just trying to share my screen here.
Yes, I can see you, and you transfer it to the full screen.
Right, welcome everyone. So my name is Martin Carolan. I'm one of the executive directors of Global Energy Ventures. We are a listed company down in Australia, and our code is GEV. So for more information, you could look us up. So we're in the business of shipping solutions for the energy transition. So we come from a background of natural gas. I'll talk to the context of that background, but we are now quickly accelerating a program to develop our own CH2 or compressed hydrogen supply chain in the form of loading, shipping and unloading. So we've seen a number of great presentations today or this afternoon, which talk about the momentum in terms of supply demand and the investment going on. And I guess one of the critical elements is around the concept of storage and indeed transport to open up those export markets. So as the background to our company, we are focused on the development of integrated compressed shipping projects. So we've been advancing our regional green marine solutions for natural gas for the last 3 to 4 years. As a backdrop to our company, we have fully developed a compressed natural gas shipping solution, both for the loading, storage, transport, and the unloading. So we are a developer of projects, not just ships. So we have what's called the CNG Optimum vessel, which has been fully designed and approved for construction and is now ready for commercialization. So that's a patented design which has been optimized for the storage of 200 million cubic feet of gas. And so in our supply chain for gas, we understand what it takes to load under pressure, store and transport and unload. So we're working with energy majors in different regions and looking to take feed level acceptance and final commercialization in the current calendar year. So last year that led us to looking at the phenomenon and the headwind or tailwinds coming for hydrogen. And so we challenged our engineering team to look at a new ship design and concept for the storage of hydrogen and transport by marine using compression. So we now have what's called termed the CH2 ship, which is in development. It is designed to take 2,000 tons of compressed hydrogen in its large capacity, and we will also look at scaling down that design to as low as 400 to 500 tons for demonstration or pilot purposes. We filed a patent recently, and we're now critically in the first stage of approval in principle and advancing our ship engineering through to what would be our first pilot project. So really we're focused on solutions for large-scale green hydrogen projects in Australia. And also at the end of this, I'll touch on what we're looking at in terms of an offshore European solution. So clearly one of our activities last year in investigating the approach to transport was trying to search out where was the market at, and it seems as though that shipping and a transport perspective is still in its infancy. So we've really only seen the introduction of a small pilot demonstration ship in the form of liquefaction from Kawasaki Heavy Industries. We've seen evidence of Hyundai look at a liquefaction ship. Obviously, ammonia is currently being shipped today. And so we've looked at the application of compression. So this is our CH2 ship in terms of its specification, as I mentioned. So we launched last year a program with the American Bureau of Shipping to go through the first stage of what's called the approval in principle. And that's really to look at both from a regulatory design point of view, an engineering point of view, and a hazard point of view, that there are no safety hazards that cannot be either mitigated through design or other methods to ultimately seek approval for construction. So we are expecting that approval in principle imminently. And so that then sets the roadmap for the next 12 to 18 months to go through a series of engineering and prototype testing activities to then come to the formal decision of approval for construction. As I've said, we've lodged a patent application that's been filed. So this ship is designed to take 2,000 tons. It's quite a large ship. Think QMAX level from an LNG perspective, roughly 300 meters long. The two tanks are 20 meters in diameter. They are nested with multiple layers. We have IP around that. So at this stage, we haven't sort of gone into too much detail how that sits, but they are essentially, two 200 meter length pipes that will store at pressure of 250 bar. Another thing that we've been doing is working on the concept of where are we going to be competitive in terms of a commercialization, volume and distance point of view. Our ship is designed to be emission-free. Obviously, that's the holy grail moving forward. So if you're looking at electric drive engines supported by fuel cells, we've done a MOU with Ballard Systems. Ballard, as many viewers will be aware, they are progressing the advancement of fuel cell systems in all forms of mobility. And shipping is one of their verticals. So they were excited when we launched to get involved. And so I guess the key for a ship that's going to be emission-free from a fuel cell perspective and the use of hydrogen is where do you store the hydrogen tanks? And on a long distance perspective, where would you refuel that? So our solution is quite neat here in that you would feed the hydrogen direct from those storage tanks. So the next stage for us is really to move through the next phase of the approvals once we get that first stage imminently and begin to start to engage with further technical partners. We are talking to some project developers and looking at end user customers and obviously governments for funding support and strategic advice. We're currently focused on the Asia Pacific, and already today we've heard some great presentations around the demand and obviously the supply side. So obviously Australia leads the world with a national hydrogen strategy. It has, as we've heard today, 5 of the world's top largest green hydrogen projects globally. We have a well-established hydrogen strategy and obviously an abundance of renewable resources. Those resources are all ideally suited to the production of hydrogen. And so cost obviously is one factor that needs to be driven down. We've heard quite a bit about that today, but definitely on a competing cost basis. So we're in a location with the largest green projects with an access to the key markets from an Asian context. And obviously we're at the low end of the cost curve and seeking to drive that lower. So, we are now aiming to put forward an alternative transport supply method using compression and seeking to export materials, a large scale tons of hydrogen from the northwest part of Australia up to Singapore, South Korea and Japan. So we're just going to briefly go through the concept of our supply chain. So when we talk about a shipping and transport solution, we also include the compression for loading and obviously decompression for unloading. So our supply chain is simple and our objective was to be as energy efficient as we can. So we obviously leverage the application of compression, which is used already. We've heard a number of attributes today where compression is applied from an onshore perspective. Compression also exists in each of the integrated supply chains for both liquefaction and ammonia. So all we do is 3 simple steps. We take the produced hydrogen in a gaseous form. We can compress and load that green hydrogen directly from the electrolyzer to the CH2 ship using compression. We load that to an operating pressure of 250 bar. And the ship is always berthed at port. So we heard some earlier conversations around storage. So effectively we use the ship as storage. So we don't have a storage requirement at the loading end, and indeed we directly load in or load out at the customer end. So from the CH2 shipping point of view, we store and transport in its pure gaseous form, and as we said, an operating pressure of 250 bar. So the ship that we're looking to seek approval for in the first instance has a capacity of 2,000 tonnes. That ship is powered by electric drive engines with onboard fuel cells, and that fuel is directly coming from the hydrogen which is contained in our cargo. So importantly, we referenced that our ship is a closed system, so there's no result in boil off, unlike liquefaction. So that is to be a very efficient ship. So what we need to do is now get through that approval process. We work with the shipyard on capital cost and improve our propulsion systems. From an unloading perspective, the ship really just unloads its pure gas, hydrogen to the customer, ideally for fuel cell applications. The ship unloads in an unassisted format, so that it arrives at a pressure and then it releases down into the receiving pressure with minor scavenging compression required at the final stages. So a very elegant, simple and efficient system, and one that we think will start to have good traction. So to determine where we sit in terms of a competitive basis, we looked at at a recent study, which we announced 2 weeks ago and is available on the ASX platform and our website. And that was to define where would we'd be sit on a competitive basis, looking at volumes of 50,000, 200 and 400,000 tonnes per annum, and looking at market distances for 2,000, 4,000 and 6,000 nautical miles. And the conclusions were to try and achieve what was the levelized cost of hydrogen. And we're talking about end-use hydrogen here for both the CO2 supply chain, an LH2 liquefaction supply chain, and NH3. And I'll talk about some of the nuances of each of those shortly. What we found that CH2 was viewed, we work with GHG on this, was viewed as a simple and a highly energy efficient supply chain. It benefits from maintaining that hydrogen in a pure gaseous form. With respect to our technical barriers, that is really contained to the ship. So we have, a 1 to 2 year process for approvals, and obviously we need to get through that as the next stage. And CH2 also has this attribute that it's an ideal solution for the volatility in the renewable generation, in the fact that it has the ability to load follow. Whereas we already heard this afternoon, whereas LH2 and NH3 processes really need that steady state of supply. So you can see here from the illustrative example here of 200,000 tonnes, that CH2 really was on a levelized cost delivered basis, very competitive up to 2,000 nautical miles, and we're still as competitive or in the mix, reaching 4,000 nautical miles. So those distances from the northwest WA up to Northern Territory and down to Gladstone, we are capable of delivering into those key markets. A couple of the key assumptions that we need to obviously emphasize is we're always looking at the concept of a constant supply of green hydrogen. We haven't focused on blue or other forms, so we focused purely on green hydrogen. So that hydrogen was provided by a third party at a constant pressure of 20 bar. At the loading location, we've included certified green hydrogen, green power grid to meet the energy requirements for either compression, the process of liquefaction, or ammonia synthesis. And then the power requirements for the ship propulsion and auxiliary power were supplied via fuel cells and powered by the fuel directly in that ship. So at the loading end, we looked at power requirements that were supplied via fuel cells. So each of the supply chains needed to demonstrate a 100% efficient green supply chain. And so the key observations start to flow through from this graphic here. The first is that all three supply chains start with compression. I mean, that compression is to lift the energy density up to an operating pressure that's required to run through its processes. And indeed, the pressure for liquefaction and ammonia is the equivalent to the operating pressure which we want to load and operate our ships. We viewed that liquefaction then starts to add quite additional extensive and intensive processes to get to the storage of -253. And also it has a reasonable level of energy use in terms of boil off. So from a shipping perspective, we haven't seen yet a scale version of an LH2 ship. Indeed, there is some evidence to suggest that the boil off could be in the 1 to 5% range. So we've used a 1% boil off in this regard. So in terms of ammonia supply chain, clearly a well-developed and accepted mature type technology, right through to the point of delivery. However, we did note that at the end user really only requires a pure hydrogen versus the form of ammonia. There is quite a few technical challenges to get through that cracking process and the purification. And indeed, it was quite a high energy intensive process. So that's not to say that the technology is not coming or it can be developed over time and at scale, but we did identify that it uses quite a high level of energy. And I guess the CSIRO and others are trying to work through that process. So overall, our key findings were supportive of all of the supply chains. We've heard today that the market, will be quite significant and large, but from our perspective, the advancement of shipping solutions is still quite in its infancy, and there are challenges from an energy efficiency point of view and some technical barriers as to when those alternative supply chains will be available. So, really supportive of compressed hydrogen, and we're now in the stages of going through some commercialization steps. So the next steps for GEV, we're now assessing renewable green hydrogen projects. So rather looking for partnerships for some of those announced projects that we saw referenced today, to look at the review and potential implementation of a CH2 supply chain, or we are looking to do a standalone project of our own to support the construction of pilot scale ships. So the graphic here shows that if we're really only focused on green projects supported by renewable energy, we're looking at projects, as I said, from the Midwest of WA up to Northern Territory and down and across to as far as Gladstone or the Townsville area. So we are now in the process of starting to progress that. So I guess in summary, if the Holy Grail is to have an energy source that's produced from a renewable source at point A and delivered to point B, it's our view that that full supply chain should be, one, as efficient as it can, and two, also utilize in an emission-free process. So with that, we are now heavily pursuing our supply chain, and we'll be making further updates to the market in terms of our progress with partners, and also evaluating further technical partnerships as we move forward. The last comment I just wanted to leave with the group with is also, we've also been talking to people in Europe about an offshore green hydrogen transport solution. It hasn't been discussed today, but obviously extensive offshore wind renewable installation and capacity taking place. So whether it's across the UK, across to Germany, down through France and Spain. So we're seeing significant build out of offshore wind farms across Europe. Not all are going to be able to connect direct to the grid. And indeed, some instances, the grid just cannot take that capacity. So we've seen discussions start to take place as well. Perhaps you convert that excess capacity into the form of a hydrogen, a green hydrogen. And then the question starts to be put through, well, then how do you then transport that to shore? So in the instances where we're talking much shorter distances, we think compression has an even greater role to play. So where there are instances where subsea pipeline cannot work, or in fact subsea electrical cables back to shore don't work, we're now starting to talk to companies that are looking at these offshore production facilities, which have the combination of electrolyzer and compression. And then so we would simply build out perhaps a smaller ship size and a fleet of ships that could load in an offshore environment, sail to shore in half a day, and then unload that compressed hydrogen in its green format. So that's another initiative we have, and I guess another emerging market from a transport perspective. So clearly the advantage of compression really starts to flow through on short distances in this regard. To be able to put forward ammonia type solutions, or indeed liquefaction, would simply be too challenging and too complex and too costly for such a short distance. So we'll look to see how that progresses over the next coming months as well. So with that, Bryce, that's kind of the end of our presentation. For anyone who wants to look more deeply into our announcements in the scoping study we released, it's available on our website, gev.com, also available on the ASX platform, and we'd be happy to take questions.
Okay, thank you, Martin. Thank you. And we still got some questions for you. And the first is, what do you think of the advances in the development of the hydrogen distribution ships and the possibility of the faster scaling up?
Well, as I said at the beginning, so when we started this journey last year, we saw that there had been some early stage advancements by Kawasaki Heavy Industries in terms of liquefaction ships. Already there are ammonia ships that are available. So as an alternative to delivering a pure hydrogen gas in an unliquid form, we felt that compression had its role. So the advancement of liquefaction is still in its early days from our perspective, but no doubt there'll be considerable capital and investment made and attempts to improve out whether an LH2 solution or indeed the ultimate solutions for ammonia and compression.
Okay, thank you. And the second one is, what do you think is the most economic way to transport the renewable hydrogen on the ocean for up to the 300 kilometers. What states, what comprise that are liquefied, or what containers, tanks and barges are in the house of the purpose built ship.
Yeah, I mean, 300 kilometers is a short distance. So we have seen, I think, it depends. If it's in an offshore environment, I mean, pipelines would always be the preferable choice, right? The lowest cost from an operating perspective. 300 kilometers is a very short distance. I guess it depends whether it's in an offshore environment. We've seen the advancement of some fleet type systems in shorter waters up in Norway, and some are on the rivers of Europe. So I think compression could stay a role, but perhaps it's more of in a barge situation. So using a short, slimmed down version of some of our tank containment systems in a barge format. I don't think 300 kilometers is a too far a distance to really warrant the development of a full shipping supply chain.
Okay, and we got another question from the Q&A live box from Josh. He asked about how does the energy content of the 2,000 ton CH2 the YSO compare with the typical the 180,000 megawatt LNG cargo?
I can't see that question. Who's it from? Josh.
It's under below from the Josh Berry.
Okay.
Yes.
Well, I guess the energy content on an 180,000 LNG cargo, I'd have to take that question on notice. So we're talking about liquefied natural gas, are we? Yeah, I'd have to take that on notice and do that calculation. I mean, offhand, I wouldn't be able to convert that, but yeah, I mean, I can take that and answer that, shortly after this session.
Okay, sure.
Yeah.
Okay, thank you, Marty. Thank you. And thank you for your presentation about the hydrogen export across the APAC and the ocean. And it will figure out a lot of issues in this area. Thank you very much.
Thank you for the opportunity, Ross. Thank you.
And now we'll finish all the session today, and by a deep understanding of the hydrogen supply chain in different sectors like hydrogen producer, supplier, storage, and the transportation and export. And thanks to all our speakers' valuable speeches and patient standby. And I hope you have enjoyed this sharing process. And also thanks to all of our attendees for staying with us until the end. And by the way, I'd like to tell you about our physical event here. Please allow me to announce our two upcoming hydrogen events produced by the Leader Associates. The first one is Japan event, the Connecting Green Hydrogen APAC 2021, Connecting Green Hydrogen Japan 2021, and it's the first international hydrogen event based in Japan, focusing on the green hydrogen supply chain and the country's hydrogen future in Japan. And the conference will be hosted about June 17th to 18th in Yokohama, Japan. And this event will gather over 500 senior executives from across the hydrogen energy value chain in Japan globally. And now the ENGIE's, Shells, and Voltalia Intercontinental Energies senior C-levels representatives have confirmed to attend this conference in Japan in June. And also another one is our Australian event, the APAC event, the Connecting Green Hydrogen APAC 2021. It's a leading green hydrogen conference exhibition, which is committed to facilitating green hydrogen supply chain and building up the regional hydrogen business network across the APAC. And the event will gather more than 600 senior representatives and hydrogen leaders from the global governments, investors, developers, the suppliers, utilities, and the technology and the solution providers to discuss the hydrogen industry's future through the APAC ocean. And especially in the country like Australia, Japan, South Korea, and Singapore and China. And at last, many thanks again for the continuous support from our sponsors and guest speakers and delegates and all the people who are standing with us during this special period. You know, the COVID-19 period is really a hard time for our business partners. And also with the target of the accelerating the green hydrogen, more and more the digital contact will be created by the leader associates, and to keep enabling the business networking and the insights sharing. And then last but not least, I would like to give the big thanks again to all of you and all of our audience staying with us in front of the screens. Hope all of you enjoy this new coming year 2021 and the business revive